Okay, excellent. Good morning, everybody. Welcome back to Foundations of Computing. Today we'll discuss a couple of different topics. We'll start with the lecture on CSV, iterators, and itertools. Specifically, CSV files is a special format of file that I will discuss how to handle it and how to read and write to it. Then iterators are a special kind of objects that allows you to iterate through containers, to traverse containers or iterables if you want, by avoiding keeping track of specific indices and in a way that allows you to perform lazy evaluation, which we'll see what that means later. Itertools is just a library that contains more of a set of functions and special iterators that you can combine to obtain more easily more complex functionalities. Okay, a few reminders here. The mid-semester test results have been released for those who might have not seen them yet. They are on Canvas and on Gradescope. The mark distribution has been also released. It is on one of the posts on Ed, post number 299, sorry. Assignment 2 was released on Monday. Please, if you haven't done so, visit the assignment tab on LMS to activate the project and start working on it as soon as possible. Grok worksheet is due on Monday, 30 September, and that's because next week we will have a break, a teaching break for a week, which will be the mid-semester break. So we will resume lectures on Monday, September 30th. As usual, just to warm us up a bit, let's start with a couple of fun facts about Python. One is that Python uses a philosophy that is called battery included, which stands for the fact that the standard library in Python has a comprehensive set of functionalities. So you can achieve really a lot by using Python and its standard library and without having to use any other external tool. And here on the slide there are three or four examples. One is OS, which is a module that you can use to interact with the operating system. IO for doing input-output of files, and HTTP and socket, which can be used for accessing the network and enable network programming. Another interesting fact, which is actually extremely convenient, is that Python has a so-called package manager called pip. So if you haven't used pip yet, I highly encourage to do so. I mean, in general, this is the standard practice. So whenever you don't have a Python package installed, you can install it very easily by using pip. Pip stands for Python installs, pip installs packages, which is a recursive acronym, the way it is defined. And installing packages with pip is as easy as going on your terminal, writing pip install, and then the name of the package, and that will get installed in your Python version. Okay, first topic of today, CSVs. Now, since this is a form of file, let's start with a quick reminder on how to deal with files, how to read files. Specifically in this case, there are a few basic methods that we have already seen. First of all, when you deal with a file, you use the function open to open the file. This function will return a file object that then you can use, for example, read on it, which is a member function the read member function will read the whole file at once in a single string. Okay? If you don't want to read the whole file in a single string, but you want to read it one line at a time, the file read lines will do that for you. Specifically, read lines returns a list of strings, and each string is a different line in our file. Now, another way to, in the two first lines of the code that you see here on the slide, we're using both read and read lines. But the idea here is that in both cases, we are reading the whole file at once. And that might not be ideal for large files, because you don't want to have all that content in memory. It might be too much. It might be simply impossible to place it all in memory at once. Memory, remember, main memory is much smaller than persistent storage on your disk, for example. So a way to around that is to use a for loop. As we are seeing here, you can open your file and then use this particular syntax for line in FP, where FP is our file object. Okay, so this is just a reminder. And then, of course, in the loop, this will read one line at a time. And then, depending on what you have to do, you can process that line, you can print it out. It's up to the specific functionality that you're trying to implement there. Okay, with that in mind, let's look now into CSV files. So CSV files, CSV first of all stands for comma-separated values. This is a very common format to store tabular file or structured data because it has a particular structure. You might have come across this because Excel opens these kind of files, but that doesn't mean that is an Excel format. It's actually a general format, okay, that can be read and used by many programs, as it is. In fact, it's quite a standard format for data science, for structured data sets. Now, the idea behind these CSV files is that because there is a specific format, people in Python implemented functions that take advantage of this structure because they know that there is a structure there. And so there is a specific package, a specific module in Python called the CSV that allows you to read and write to these files quite efficiently. And plus, of course, a bunch of functionalities have been built on top of it. In terms of the format itself, you can see it here on the slide. We have a first row in our CSV file, which is called the header. And in the header, we have the labels for each one of the columns in our CSV file. And then each one of the rows has the associated values for those labels. It's a very simple format. Each value is separated by a comma, and then each row is on a different line. Okay, so a common way to handle CSV files is to convert each row into a dictionary. That's handy because the keys in your CSV, in your dictionary, can be made the labels of each one of the columns. So what you will end up with is essentially a list of dictionaries in the end. So let's do this together, just to demonstrate it. So let's say that we want to read a CSV file that I have here. What this CSV file has in it is the amount of rain, the millimeters of rain for different cities that we have around the world throughout the year for 12 months. Okay? So I want to read this. The first thing to do is to import the CSV module so we can access the functions which are defined in the CSV module. Then, as usual, we define the file name to be the name of our file. This is in my directory, so I can just write rainfall.csv. Okay, once I've done that, what I want, as I said before, I would like to have a list, which is a table, and each element in the list is a dictionary. So let's declare our table here, table as a list, and then for line in, and now we need to open the file, and when we open the file, we use a special function from CSV that allows us to directly transform each line into a dictionary where the keys are the labels on each column. Okay, so and this function is called the dict reader or dictionary reader. So CSV dot dict reader, and we need to give it as an argument the file. Okay, so the file object, and to do that we can do that in a single line by using open directly on our file, and this is in read mode because we are just reading the file. So file name, right, and then all I have to do here is to append the lines, right, and the dict reader function will do everything for me. So it's passing directly each line as a dictionary. So let's try to print this out for, let's say, row in table, which will be each one of my entries in the table, but it represents a row. Then I can print the content of this file. So let's say we can use F strings. We can print the city, right? So the name of the city will be simply the entry in row of our city, right? That's the key. And we return the name of the city. And then, for example, I don't know, if you wanted the December rainfall, they're ready, right? Yes. You do the same, select the row, and the entry is going to be just the key, which I think is spelled this way. We can check whether it's December that way. Yes, it's with the capital D. And we can run this, and that's the result that we get. Okay? So pretty handy. Now back to our slides. So that's one way to do it. Another way to do it is instead to simply read by using a list. So specifically by mapping each row to a list. And this method is more memory efficient simply because we are avoiding the overhead of defining all the keys and storing all the keys multiple times. Because remember, when you have all those dictionaries for each row, the keys are going to be the same. On the other hand, is obviously less readable because now you need to remember each element or each index in your list for each row, what it maps to, right? Which one is the corresponding label? Yes?
Is there a special data type in Python, which is like a table, where it has the best of both worlds, where, like as you mentioned, it's inefficient to store all these separate dictionaries when the keys are just the same data repeated over and over again. On the other hand, if you're storing it as lists, as you say, you need to remember the indices corresponding to each key. So is there a special data type which just stores the keys once and does that work for you?
Yeah, so There are more complex data types which are defined in other libraries, such as pandas, which are designed for data science. And the first one that it comes in mind are data frames, where they actually implement those functionalities, yes. And they are more efficient, and at the same time allow you to look up directly with specifically the key by storing it once. But that's much more complicated, right? Because you have to have implemented an object that actually, it's a more complex data structure. Okay, so just in this case to show a bit what's happening and how you do this, instead of using the dict reader here, dictionary reader, you can, oops, what did I do? You can just uncomment this, and then we can do full line in CSV. And now we use the simple default reader from CSV. You give it the file name. And then just table append the line. Now, obviously here, now we cannot read, we cannot print things in that way anymore. We will have to specifically specify each one of the rows in the table and specify also each one of the indices and remember which one that maps to. So you can see how this is not great. So let's do an example of that. Let's remove this. Let's say rain, full, in city. And then we have to take our table here. We still need some formatting. Let's say, for example, I can take table, then I can use a double index to index all these different lines and the entries in there. So let's say, I don't know, I want to print up to 5 here. Let's see. What did I do? Oops. I think that's, no. That didn't want to work, maybe I made a mistake. So in general, this will be a huge table. So obviously, if I go, let's say, from the first index to the 13th, I might have some problems of format here. What am I doing? Table. Interesting. Oh, I'm iterating over the rows. Apologies for that. So I'm already iterating over the elements in the table here, which I shouldn't, because this is accessing now each element in the table. So we cannot use that for loop. That's where this was getting tripped. I'm not sure whether it's a problem of VS Code. Okay, I will have to come back to you on this. I am. Oh no. That's it's just somehow reading the name. Okay, I will have to come back on you on this. I'm not sure what is happening, whether there is a problem with my VS Code on this one. I probably have done something wrong here that I cannot see at the moment. Apologies for that. So this code here itself, or maybe it's the file. Somehow it doesn't like the string formatting. No. Okay. Oh, sorry. Yeah, that's not what we want. Was there already? No, I don't think so. It's doing something a bit interesting at the moment. I don't understand.
Is it because the strings are being stored as lists? Like lists of characters? Lists of characters?
Yeah, it might be that. That might be a possibility. I need to. Oh, that's a stupid mistake. I don't know if you see it here in the reader.
Yeah.
We didn't open the file. So it's using directly the string, which is file name. And so you can see how easier to do something really stupid, as I did. I'm sorry about that. But now we finally have access to our list. So the problem there, again, repeating, is that I was not opening the file. So the weird characters that we were seeing were because we were reading the file name, and each one of the entries within our list was just a character in the file name. And that is why I was struggling to map those characters back to what I had in the file, which were completely different characters. Okay, but definitely this shows that this, to a certain extent, that this way of reading things, it's not ideal because you have to mentally keep track of the labels for each column. Is this clear what happened here? Yes? Okay. Back to the slides. Okay, so in some cases, we will need to skip some of the lines in our CSV file. A typical example would be when you want to skip the header, for example, or you might want to skip a certain number of lines because you know that they don't contribute to the data that you want to process. Now, one way to do this is to read the whole file, right, and then use slicing, which is a bit of the obvious thing to do. But obviously, this will be as the usual problem of inefficiency associated with the fact that you need to put all the file into memory. And anyway, let's look at this. This is essentially what we have been already doing here. So here what we are doing is exactly that. We have been reading the whole file in the for loop, and then we use slicing. Now, if I wanted to access the file starting, the table starting from a particular index, I just use slicing, right? And again, so this is printing from each one is printing from line number 2. Let's actually double check this. So it's printing from this line in our CSV file. So if I want to skip the header, say, I can just do this, right? And you can see that I'm printing from Sydney. So it's a list of lists, which each entry in our list is a row, but that row is a list with all the entries in there, with all the words essentially in there. Okay, another way is, which is going to look more complicated to you now, is to use what we call an iterator. And this serves a bit as an introduction to iterators. Specifically, how do we do this? Well, one thing that we can do is, first of all, to use our context manager here to open the file. We get a file object, and then we can provide that file object to our CSV reader function. Now, the reader function, returns a specific object, and that object is under the hood something that we call an iterator. So what we do here in this loop is to use this particular notation with the underscore to say that we are not going to use any of the elements in that loop. So we basically put a placeholder there. This is just for readability. You could have put any other variable. But for readability to say, and for the programmers to understand, I am not going to use the elements of that particular loop. So for underscore we range 3, and then we use this special function called next on reader. Now, what you can imagine is happening here, every time I use next on reader, I am going down one line in my file. I'm not doing anything else, just every time I go next, okay, it's essentially doing one line, proceeding one line down in the file. So I went down 3 lines here in this particular loop, so I skip the first 3 lines, and then I can use my traditional loop to say 4 line in reader, and then use our table append as before. Okay? Now, obviously, this is a better way because we avoid reading the whole file at once. Potentially, here on this line, I don't really need to necessarily append, right? So this example, I'm just appending because I want to have a table with all the content and each element in the table be a row in my file. But in other cases, I might just be processing things, so I don't have actually to store anything. And so that's a better way of doing things in that particular case. Okay, so this brings us to this iterator topic, right? We have one here. It looks like, at the moment, a bit mysterious, so we are going to dive deeper into iterators to understand what these things are and how they work. Yes?
So this is to be more memory efficient. But in the earlier example, you had 3 cases where you're opening the file back to back, and you say this is kind of bad because you don't want to open the file 3 times. It will take up memory unnecessarily. Is that correct?
So you're doing 2 things. You're opening the file,
yeah,
and then you're reading all of it and putting it into an object.
Right.
That's the part where it's memory inefficient.
I guess my question is, if you've already gotten open file name as F, so you're creating a file object,
yes,
has it not already read through the whole file, and therefore, what memory is being saved by using this technique?
Right. So the answer is no, it has not read the file at that point. And this is one of the key things that I'm going to show you under the hood what's happening here. So it turns out that F, so the object that open returns, I said it's a file object. And under the hood, that file object is also an iterator. And iterators have this advantage of lazy evaluation. So it's not reading the whole thing. you can think of it as just keeping track of where we are in that file.
So by itself, there wouldn't be any memory cost to opening the same file a bunch of times, as long as you're not reading through it yet.
Correct. You can open the file. It's not going to use up any memory except keeping track of a very small object. But then when you're reading, the problem is you're bringing it into memory. Okay, in order to understand what iterators are and how they work, since they have to do with iteration, what we need here, this is a very irritating thing. Better. So we have to understand, we have to remind ourselves about loops, okay? So we have been dealing with two different kinds of loops, for loops and while loops. In a for loop, we can see here that we are keeping track of the elements within an iterable. In this case, the iterable is this list, 1, 2, 3. And then we can print each one of the elements each time. The equivalent while loop is more verbose. And it has much more manual management. We have the same iterable, which is this list, 1, 2, 3. Then we have to initialize an index to keep track of where we are in the list. Then we have the syntax where we say while index is less than the length of the iterable. We print, and then again explicitly we need to take iterable and index it. So we use indexing there. And then increase the index. Once we reach the length, here the loop will break because the conditional for the while will become false. Okay? So what are the things here? If we want to abstract away this behavior, what are the main things that we need to keep track of? Index, 1. Then? So let's try to simplify this as much as possible. I'm going to tell you there are 3 things we need to keep track of.
Which part of the iterable you're at?
Okay, yes, which I guess it's index, so, but there are 2 things, right? So let's actually call that current index, which puts together index and which part you're currently at.
So you need to know what the next index is, or?
If you have the current one, you can keep going, right?
Okay, so you need to know the current value. Is that 1 to 3? Or is that just something you're accessing?
Oh, the value is important, right? So how do I access the value?
With the index, right?
With the index, but where do I put it? I need to have the object. I need to have the iterable itself. Otherwise, I'm just iterating through indices, but I don't have the object. So I need to have the object, the iterable. I need to have the current index.
Would it be the initialization and then also the check to see if it's less than something?
Okay, so initialization, I guess, if you have your current index, you, at some point, you are starting somewhere, which is your first. So your current index, you can imagine that goes from where you're starting. But yes, there is an important thing, which is your end condition. Okay, so iterable, current index, end condition. These are the 3 things we need to keep track of. Okay, and these are here. Now, what iterators do is to keep track of these things for you. So it is an object which is defined to keep automatically track of iterations when you traverse an iterable. And now we're going to go a little bit more in detail in that. So here is the definition. An iterator is an object that enables you to traverse, so to go through the elements of a collection this collection, we have called it iterable, things such as lists, tuples, or dictionaries, without maintaining explicit control of the counter or index, the way we called it. Okay? Now, there are three main concepts here that there are in this definition. There is the object, the idea that an iterator is an object, okay? So I can assign it to a variable, I can manipulate it, I can pass it to a function. It's an object. It serves to traverse, which means to iterate sequentially through containers, which is the third word. And container is a generic word for a collection of items. For all intents and purposes, we have called containers iterables. But we will see that there is a slight distinction between the two. This is not very important for the sake of the course. In general, container is a better term, is a more general term, because there are containers that technically are not iterables. Okay? But no one is going to tell anything if you just call them iterables in the specific setting of this course, because it's a slight distinction, and we won't go into those more advanced part functionalities and objects, I would say. Okay, so all iterables, such as list strings, tuples, and all the ones that we've done so far, can produce an iterator. And the way to generate an iterator is just to call the function iter on our iterable. Then the idea is that this iterator will keep track of the current position in our iterable, okay? And whenever we call a next on our iterator, it is going to give us the next value in that particular iterable. Again, try to remember the distinction between iterable, which I will make it quite clear soon, between iterable and iterator. Another important thing is that iterators allows only forward traversal. What that means is that every time you call next, you cannot go back. So you have a sequential traversal of the container, of the iterable, but you cannot go back. So, yes?
So when you use a for loop,
yes.
is that implicitly calling the iter function?
Yes.
So you can
so
go backwards through
now we are discovering many things. I will go less explicitly into that, but yes, you're moving forward a bit in the lecture, and yes, the for loop in Python is implemented by using iterators. And what that means is that whenever you run that for loop on a particular object such as a list, it means that that list somehow needs to be able to give it an iterator. So a simple example here, let's do it directly here. For example, I have a list, 1, 2, 3. Oh, well, I don't have anything because I haven't called the interpreter. I have a list. And then if I want my iterator, I just call iter on it, right? And this is going to be a special iterator, which is a list iterator, because it's defined for a list. And then every time I call next on this thing, on this object, let's do it this way, next, and we have our iterator, we get the next object. Once we are done with it, we raise an exception or an error, which is called the stop iteration exception and error, which is what is keeping track of the end condition that we were discussing earlier. So to end the iteration, whenever you call next, the iterator object will raise an exception, which is a special exception that we can catch, and then continue the execution, for example, after a for loop. Obviously, you can define these iterators for other objects, right? So let's say we have a dictionary. Oh, let me clear this. We have a dictionary. Dictionaries are a bit annoying because I need to define keys. What did I do? Oh, the wrong syntax, right? And then I can define my iterator for the dictionary as well. Right. Now, this one is going to be slightly different because, as we know, when we iterate, typically on dictionaries, if we don't use the items function, we iterate over the keys. And this is actually reflected in the type of this iterator, which is a dictionary key iterator. Similarly, I can define a set, right, this way. My set, can define an iterator for my set. I can call next on it if I want. Let's just print the iterator is a set iterator. And then we can print and traverse our set. Right? And so on and so forth, right? So this works for all the iterables. That's the definition of it. Okay, so now an important, we basically did this already. We looked at the fact that the iterator itself is an object with a next function, and every time we call next, we access the next item, and when we are finished with our container, we stop, we raise this exception that I can catch with an accept block, right, and do whatever I need to do. It really depends on the implementation of our iterator. But that is the signal that I finished my container, right? And I cannot go back because, again, the iterator traverses only in one direction. Now, an important thing is that an iterator, technically, an iterator is an object that is defined by the fact that implements two methods. And these two methods are this iter method and the next method. Now, we looked at the next method. What does the iter method do? The iter method, you see this strange notation which has a double underscore. This is because are called magic methods in Python. They are special methods. They are used in a more general way by Python. That's why you use this underscore, is to avoid overriding. And to call that method, usually you don't call it as a member method of that class, of that type, but you call a generic function, which Python has already implemented for you, and in this case is the iter function. Very similarly to what we did here with next, we have called the generic function that on that particular object, which is the iterator, we are not calling iterator dot underscore underscore next, etc. Okay? And this is a feature of the implementation of Python. Why does it do that? Well, the reason is actually quite simple. This provides a generic interface for Python to apply iterators in many different places. So one of the places where iterators are applied is what we were saying earlier, in loops. Okay? So in a loop, you need to have, for your iterable that you're looping over, the function iter to be defined, because it needs to return an iterator. And that is done implicitly, okay? So another, in terms of the features of, so that's iter. Once we call iter, in terms of the protocol of how this object works, right? We have the iter function. If we call iter on a particular kind of object, it should return an iterator. Once you have our iterator, we need to have a next function that allows to keep track of the index. And when we call next on the iterator, is going to give us the next object in the sequence. And also, once we are done with it, okay, once the iteration is complete, it has to raise a stop iteration exception. That's the definition of the actual object. Now, since we have all the definitions of this object, we can define our own iterators. And here is pretty much how you do it. So in this case, we are defining a very simple iterator, which we call counter. And as all objects, this is a class. You need to use the class keyword to define that object. As all classes, and you've looked at this before, earlier in the course, you use this function called init to build objects of that kind. So the class, remember, the class is the generic template, okay? But then whenever we define an object, like down here, we are defining an instance of that class. And in this case, all this iterator is doing is give us numbers that go from the index low to the index high, okay? So the two parameters are low and high to define the object. Then our function iter here, remember, functions in classes need to take self, which is a reference to that particular instance of the object, returns just self, because that's the definition, right? In other cases, the iter function might have been defined differently, okay? But in general, the high-level definition is iter needs to return an iterator. Now, this function is, this object is an iterator, so it's returning itself. Then next is just, what it's doing is to check whether the current index is larger than the last index, which is high. So if current is larger than than high, yes, then erases a stop iteration exception. Otherwise, we do two things. We first, in this case, increment current, and then return current -1. And this is to keep track of edge conditions, such as the very first iteration. Now, what's interesting here, perhaps let's just define this function, because I want to show a couple of things. Yes, and Okay, so now we are defining counter here, and we have this. Yeah. Ooh. Yeah, that needs to be that. Thank you. Excellent. Okay, so we're defining counter here, and we are just defining the object itself here. But one thing that is important is that we can define the iterator of counter, which is an iterator, by calling iter on it. Right? And that would work equally well because it's returning self. For example, let's try this. We can directly call next on the iterator. And so, for example, in this case, next has returned the first index. Again, this is it's a specific case. Iter is returning the object itself because it's an iterator, but that's the definition. Again, so if you have a different object, a different class, such as list, then you can imagine that your iter function might need to do more work, because then you want to return a list iterator, which is what's returned when you call iter on a list. Okay?
Why is iter necessary when you have next, right? Because take this example, ultimately all you're trying to do is return the current index.
Well, I guess in this case, this is a very basic case, right? But in case of lists, you want to return in general an iterator, and it's a different kind of object.
I'm just trying to understand why that is, because if you were to define next on a list,
yes,
could you not simply define it in the same way here and just say index, like list index plus one or whatever?
We've still got like 40 slides to go through, right?
Yes.
Okay, should we continue?
Yeah, we can go ahead, but that's... Okay, so iterator. I mean, in general, I'm happy for you guys to make it as interactive as possible. We can go through the content at the right pace. Okay, so we have defined the custom iterator here. Why do we want to use iterators at all? In general, the reason is quite simple. You want some memory efficiency, so we are not storing the whole sequence here. We are going through the sequence by using an object that just keeps track of the current position. And then once we go off and finish our sequence, we raise an exception. It is in general, so what this means is that for files, as you have seen earlier, for files, we can iterate over the position in a file, right, without having to read the whole file at once. So this is much more memory efficient. In general, once you have defined your iterator, because the iterator itself keeps track of all the logic which is needed for the loop, it is less error prone. And then, in general, the idea is, which is a general idea of Python, is that allows for lazy evaluation. What that means is that, as we have already discussed, when you run a for loop, that's actually not evaluating at that point specifically the whole sequence, but what it's doing is defining an iterator, and then within the loop, every time you call an instance of that particular object, the element in the sequence, the iterator is calling, you are actually calling essentially the next method for the iterator. And so the evaluation happens at that point. Yes?
Can you use them to traverse backwards like in reverse order?
No. So again, as I said earlier, Iterators, you cannot go backwards with iterators. They allow you to go only in one direction in the sequence. But I guess you can define things in a way that you invert your sequence. Okay, so here is just to consolidate a bit the difference between iterator and iterable and iterators. So now we finally have a definition for an iterable. An iterable is any object that can return an iterator. Okay, so it's actually defined based on an iterator itself. Examples of this, we have seen them already, lists, tuples, dictionaries. You can pass an iterable to a function called, to the function called iter, and that will need to return its iterator. That's the definition of the iterable. The iterator itself, instead, is an object that keeps track of the next value in our sequence. It is defined by implementing the iter and next methods using the iterator protocol that we have discussed earlier. And we have pretty much done this. Okay, so here there was a clarification that somehow we anticipated, and that clarification has to do with the fact that now most of the mystery around these loops and also file objects is unveiled. In practice, whenever you're calling with, as in this case, open and with this notation as file, I said the file is a file object, but in practice, what the file object is an iterator. It's a special kind of iterator, okay? And so iterating over it just yields one line at a time. And that's why you can use then that particular loop. And so this is memory efficient, and we discussed why it is. Now, before we go through itertools, I'm going to give you a few minutes of a break, and then we'll do itertools and recursion. Okay, I think we're going to start again because we don't want to run out of time. So let's discuss. Oops, my mic is off. Now let's discuss. Yes, this works. Let's discuss itertools. Itertools is just a library that provides additional functionalities to manipulate iterators. It provides also iterators which are much more complicated and they're implemented for you. And the key features of the library itself is that, the same philosophy as iterators, but just more complex. So they are memory efficient, they do lazy evaluation, as we have seen for all iterators, but they implement more complicated functionalities. So in general, you will hear that itertools implement what we call an iterator algebra, which means that you can compose the iterators in itertools to achieve more complex functionalities. They are compatible between each other, and they are composable. So the first one they're going to look at is this product function in itertools. This computes the Cartesian product of input iterables. Okay, so this means that all possible combinations of elements from multiple sequences that you provide product will be produced. So let's look at an example of this. In this case, we are using this function that provides us a deck of cards. We have done this in the past, and we are going to do it in a different way now by using the product function in itertools. So let's grab this code and explain it in our VS Code. So the first thing to do is to import from itertools product. We define this function deck of cards, We have our suits, which are clubs, diamonds, hearts, spades. Now they are defined as a single string, okay? The same for the values. They are defined as a single string. And then we define this particular object, which is whatever is returned by product, which is a special kind of iterator. And we give product the values and the suits, and that is going to do the Cartesian product. So it's going to couple all the characters in each one of the strings with all the characters in the other string. Now, because it's going to be provided as a pair, we join, as two different strings, we need to join, we need to join these, the two characters coming from this string and that string, right? So we are using the join function. This is a typical use of join. We call it as a member function of the null string. And then here we are using simply list comprehension to generate all the cards in our deck. Okay, so let's try these out, and we can use directly the notation that we have here to make it faster. And so this, let me make it bigger. Oh, let's do it this way. Clear. So in this case, we get the first 5 cards in our deck. Okay. So quite simple, this one. Now let's go over the cycle function. What we do here is to provide a function that allows us to cycle through an iterable in an indefinite way, okay? And so this is typically useful when you have to do, for example, a round-robin scheduling or repeating actions in a loop multiple times. And so an example that we have here is how to deal cards to 4 players in a round-robin fashion. And this implementation uses our implementation of the getDeck function that we have just defined. So let's grab this as well. And see what's going on here. Now, one important thing is, well, let me just do the indentation quickly. So one important thing is that now we are using this cycle function, right? And this cycle function, it's not defined at the moment because it's part of Iteratools. So we need to import it also here. Okay. All right. So here we get our deck of cards. Then we have 4 players, and we represent the 4 players and their hands as a list of lists. Okay. So it's a list. The 4 sublists here represent the hand of each player. Then we call players, and we define this players variable by calling cycle on hands. And let's see what this will do. So basically, we run, we loop over the cards in the deck. Okay. Then we define player as as a variable which is given by next in players. Okay, what that is going to do, okay, each time we call next, we are cycling through these sublists. Okay, so player here is going to be, each time we call next, a different sublist here. And we cycle through that in an indefinite way. For each one of the players, then we append a card to them, and then we return hands in the end, which will be our list of lists, which will be filled with the cards that each one of them has. Okay? So let's try this out. So as you can see here, so what we are doing now in this particular remainder of our code is to use enumerate. I don't know if you have seen enumerate before, but all enumerate does is to return both the index, okay, of an iterable as well as the value. Okay, so we have the advantage here that we can return an index. We can tell enumerate where the index should start, and in this case, this is what this one is. So as you see here, when we are printing out, we print starting from 1, so player 1, which is this I, which means that I, instead of starting from 0, starts from 1. And that's because I have given as a second argument to enumerate the number 1. And then there is the usual list manipulation here with F strings. Okay, excellent. Next one, they're going all in order of complexity, is group by. So group by allows you to group consecutive items in an iterable based on a key. And this is particularly useful when you want to group elements in a sorted sequence. So specifically, the important thing is because it's assuming that the sequence is sorted, group by, you will need to provide an iterable which is already pre-sorted. That's the assumption that group by is using when you're calling it. And so now we're going to use these, again, learning by examples here, grouping cards by their rank. What do I mean by rank? By rank, I mean not the suit, but the value, okay? So I want to have groups of cards where, for example, all the cards that have value 2, or all the cards that have value 3, all them grouped together. And in this case, I'm using this particular hand, which represents one of my hands in the game. Let's remove this. So I have this particular hand. And when I call a group by, what I want to do is sort this hand, because otherwise it's not going to work for what I said before. Now there are two ways to do this. One in the slide is to use sorted. I can also do just hand.sort, which will do the sort in place. Okay, we've seen this. And then we have a loop where we run over the rank. Sorry, I forgot to import as also group by. So we run a loop over the rank and the group, which is ultimately what we want. And then we call group by, which gives us a special iterator. Now, what do we give here? We need to give it the sequence. In this case, is a list which has been sorted, so hand. And then we need to tell group by how to form these groups, right? Based on what? And in this particular case, what we're saying is that the groups should be formed based on the first character of each string, right? Because that represents the ranks, is essentially the value. So if I do that, I could define a function to specifically do this, right? So in the slide here, we are defining this first function, which just returns the first element of that string. But we have also learned that we don't really need to do that, given that that function is defined only once. I can give it a lambda here, where the lambda, the parameter here, x represents each element in the sequence, and just return x 0. And then I can print this. Let's see if I can grab the print statement here to be faster. And so now, given our particular hand, as you can see, we have formed the different groups, which are all grouped by different ranks. Is that all clear? Seems so. I will go through this a little bit more quickly in the interest of time. So another function that is defined in itertools is combinations. This generates all the combinations of k items from n elements without repetition. Okay? So for example, here in this example that we have on the slide, we have a list which represents all the aces in our deck of cards. Then we use the combinations function here. We call it with the first argument being our list, and the second is based on how many elements we want to combine at a time. Yes?
So if you use this function, it's a little bit like whatever list, in this case it's aces, right? But it could be a much larger
Yes.
list. And it's almost as if you had a deck of cards, and what it's doing is it's drawing the cards from the top of the deck without replacement, right? Because you can't have the same two.
That is correct,
values.
yes, is exactly
And
what
then
it's doing.
giving you every possible combination that you could get.
Correct, without repetition, so without replacement.
But if suppose that you had like 2 aces in that list,
Yeah.
would it be like a set where it removes any duplicates, or it will give you the duplicates, like to show that that is more common? If that makes sense. Like if you had another.
Oh, in this case, each element in the list is assumed to be a distinct object.
Right. So it could give you
Yes.
the same
Yes.
combination.
Yes. Okay, excellent. Next, another bunch of functions here, permutations. I mean, you can read up what this means, but it generates all the possible orderings in a sequence here, where the order in which the objects are placed matters. That's the definition of permutations. Slices an iterator by specifying start, stop, and step values, so allows you more fine-grained control on the iterator itself. And chain allows you to combine multiple iterators when you want to iterate on multiple sequences. Oh, no, that's me that I am going through this. Okay, so I will reserve this class exercise for later, if we have time. Otherwise, I will run through this on Friday. And the reason is that I would like to jump on the recursion first. So that's the third topic of today. It's actually not that long. It's just that it's different. So recursion is a fascinating and elegant topic in general in computer science. And it's a powerful tool for solving problems that have a particular structure. And the way we'll see soon works is that we have to use recursion, take our problem, and break it down into smaller simpler instances of the same problem. So let's start understanding what iteration is about. So far, we have solved the problems in general by using for loops, while loops, and in general, again, a more sophisticated way of iterating over objects, such as comprehensions. Now, imagine that we didn't have any of this. No for loops, no while loops, no comprehensions. And let's consider this particular problem. Suppose we have a list of booleans here. Each boolean represents areas of the Great Barrier Reef. When it is true, it means that that area is bleached. When it is false, it means that it is healthy. It could have been any other example, to be honest. And what we would like to do here is to provide a function that returns the number of true values within our list. And we want to do this without using loops or comprehensions. How do we do this? Any idea? That's hard at the beginning, right?
Like by induction.
What do we do?
So I think it's like a function. So you have your line of function, and so you can use it like.
So let's think about what we need to return. Yes, there's another way.
Since we're not allowed to use a loop, I feel like we need to mutate the data itself, right? Because if...
You're not allowed to mutate the data.
Well, we can't mutate the original data, but we can mutate a copy of the data in some sense. Or we can get a subset of it, right?
Yes,
Like,
that is true.
Like the issue here is we're not allowed to like keep an index. We can't keep a count, variable and then go through the list. So
Correct.
the only thing we can do is when we find a true,
Yeah.
right, then go back and look through the list minus that value. And so we're going in a cycle still, but it's a different kind of cycle where we're looking at a different portion of the list each time.
Okay, so I think there are a few elements here. So the first one is, yes, we need to look at each element of the list and somehow find a way to combine those elements because each element is a sublist, right? So let's say one inefficient way of doing this is to do it explicitly, right? So in this particular function, what I do is to take the length of the list, right? That allows me to decide how many of these lines I need to write, and specifically which case. So if the list doesn't have any elements in it, I just return 0. So n is 0. If it is 1, I can return the first element. It could be true or false. Remember that true or false is treated as an integer in Python. So true is 1 and false is 0. Then if n is 2, I keep going. So I take the first element, again, is a sub-list to all intents and purposes, and then sum that with the next element in the list. And I can have n of these. I don't know what n is. So you can see here that maybe I can write a very big function that supports for very large n, but this is going to be really a lot of code, okay? Whenever you see code like this, that's a bad sign. So this is called in different ways, is also called boilerplate code. In general, repeated code such this is a sign that you should modularize your code, right? So you want to take the repeated patterns of your code and make it a function, typically. And here there is the associated principle, which is don't repeat yourself, the dry principle of programming. Write functionalities, more general functionalities, only once and reuse them. Okay, so how do we do about doing this in a bit of a better way? So if we look at our function earlier, what we realize is that except for the case of 0, where we just return 0, all the other cases are actually very similar. So we could think of having the first function, this function count, and then let's say define another function. Okay, so we abstract away whatever the rest of the code was that does that for the remainder of the list. So here, this function, the idea is that count handles only the first element, okay? And count list handles the rest. But one thing here that we might realize is that count list in reality is doing something very similar to count. So the question here is, can count, instead of calling a count list, call itself, call again count? Okay? And the answer is yes, this is allowed. And in particular, this is what we call a recursive solution. A function that calls itself. So whenever count, from Python perspective, the fact that count is calling itself, it's like calling any other function. It has the address of that function in memory, and whenever it counts itself, it just goes back with the new parameter values and executes that function. Okay, so in this case, what we're doing is dealing with the first element, using count on the elements of the list, the sublist, which contains all elements but the first one. Then count is being called on this list. Under the hood, we are going back here, okay? We are going back in, and then we are doing this check, and we are returning again this. Now, for the first, for this time that we called again count, well, the first element here will be the first element of the list without the very first element. So the first element will be the second now. And we are providing the list, which starts with the third element again to count. And then we are going back in, and again, and again, and again, until we reach the point where we are calling count on a list that has length 0. And that's the return. That is called the base case. Okay? So, to understand a bit how recursion works, all recursive functions have two essential components. They have a recursive case, which reduces the problem to smaller and smaller instances. And we have a base case that essentially you can solve immediately and provides a stopping condition. Okay? Without the base case, recursion will recur forever. And in fact, that will make your program crash, typically, because you will run into an error called the Stack Overflow, which is a bit complicated, but the idea is that you don't want to do that. Okay, so the base condition is essential. Now, when is a good idea to use recursion is when your problem is you can easily define or more elegantly define your problem in terms of recursive calls. Here there are some examples that might work. Whether they are the best use of recursion, probably not, to be honest. It's just examples that work. I will provide examples that probably are better suited. So here, for example, we could think of doing the length of the list recursively by defining the length of the list as 1 plus the length of the list where we have the sublist, again, as we did earlier, with all the elements but the first one. The maximum function, this works because the maximum of a set is certainly the maximum of the first element, between the first element and the maximum of all the elements in the remainder of the list. And so you can apply this principle to define it recursively, and the minimum very similarly. Now, in terms of this is what I mentioned before, in terms of the main elements of recursion. What we want to do now is to have a simple but pragmatic case of recursion that we can do together, okay? So what we want to do is to define a function, recursive function, this is a typical example, a textbook example of recursion. We want to compute a factorial, which is indicated with this n exclamation mark, recursively. Just to clarify maybe a bit of what a factorial is. So a factorial is defined as the product of n times n minus 1 times n minus 2 until I hit 1 times until I hit basically the base case, which is 1. Okay, so I reach 1 and then that is done. Another important definition is that the factorial of 0 is by convention defined as 1. Okay? So if I want to compute this factorial recursively, okay, let's define our function. Def factorial n. I realize here that, for example, if I look at this definition, right, the factorial of n, right, equals n times the factorial of n minus 1, right? That's our recursive definition. So we have the recursive definition, we need the base case. Without base case, we are not going anywhere. So based on this, how do we define this function? Yes?
If else with a base case and a normal case.
Okay. The first thing is base case with all recursive functions. So if
I'd say n equals 0 and then return 1.
which is the smallest case that I can deal with and return. And then now we need to deal with the other case. Go ahead.
Okay, so I think you can do part, if it's more than one, obviously, if n starting from the start or in the middle is still larger than 0, without being modified yet, it's going to
So look at this definition here.
Can you return in the middle of it? Like,
Look at the definition here. So can I, let's actually do it this way. Look at this. So this one, I can write it as factorial n, right? I'm writing the same thing, yeah. So this one is factorial n equals n, right, times, what's this? Factorial n minus 1. And that's the recursive case, okay? So we just have to put it back together. N times factorial, or let's do it with a good formatting, of n minus 1. Done. Okay? So what is happening here, I mean, we can try this factorial 3. Oh, that's a usual problem with this. This is 3. Oh, we need to print this. Okay, and so it's giving us 6, which is the correct number. Now, that's not a surprise, obviously. The main point is trying to understand a bit more what's going on here. So that's the implementation. Okay, I think pretty much we understand, but that's a visualization of what is happening. Okay, so if this is for factorial 4. So I call factorial 4, then factorial 4 calls factorial 3, which calls factorial 2, which calls factorial 1, which calls factorial 0, that hits the base case. And then we go back up the call stack, returning all the values, which are all...
The stack. The function calls it the stack.
Yes. So this is called the call stack, which is all the functions that are being called. And then since we are returning each time with the multiplication, we get the final factorial. That's what's going on. Okay, so when do we want to use this recursion? Well, typically you want to use it when you have problems that are conducive to it, which means that you can easily define as recursive. 2 examples here are the Fibonacci numbers, which are defined as the sum of, each Fibonacci number is defined as the sum of the 2 previous Fibonacci numbers. Then we have, in general, other recursive definitions where each element in a sequence is defined in terms of previous elements in the sequence. These basic cases that are a bit of a no-brainer. More interesting case. Let's look at an example which is more complicated. So in this case, what we would like to do is to calculate the number of ways to make up an amount n by using coins of a certain denomination. Okay, so here the denominations are 1, 2, 5, 10, 20. The curly braces indicate a set here, but not a mathematical set, not a Python set. Now, if I want to do this with for loops, it turns out to be actually quite verbose and complicated. Do we understand what you're trying to do here? So let's say that n is 20. I want to know what are the number of ways I can make up 20 with those coins, or multiple of those coins. So there are many combinations here. So this is the solution by using for loops, okay? So what we are doing here is to loop over all the denominations, okay? We'll loop as many times as, if you see range where it's going, is n integer division and the denomination. So these numbers are the denominations, okay? Because obviously you can make up n only an integer division number of times with a specific denomination. So I can make up 20 only with up to 4 5s, for example, if 5 is my denomination. And the plus 1 is needed only because range is exclusive, right? So I need to exclude the last one, but I need to go up to the number of times I can make up n with that particular denomination. And then I can, for all the denomination, you can go through this. It's going through basically all the combinations. Many of these combinations will not make up n, okay? And then if the combination makes up n, we are increasing this counter. Now, obviously, this is not a very efficient solution. If I have more denomination, these things grows more and more, and it's also combinatorial in complexity. So how do we do this? For example, using a recursive solution. So in this case, these are cases where recursive solutions might be more effective and more elegant. Let's look a bit at the idea here. So first of all, obviously, we want to define a function. We call it answer. That's the function that is going to give us the combinations, right? The input, we have two parameters. N is, which is the n that we want to make. And then we have, in this case, is a tuple with all the denominations. Now we need to think how to do count these combinations of all denominations recursively. Now one thing that I can do is to take the first denomination, okay, and say I am going to set the number of times I use that particular denomination. For example, I have 20, my first denomination is 1, and I say that I'm going to use 1 only 0 times, so never. Which means that now I need to solve the problem of finding all the combinations, okay, that make up n with the remaining denominations. Okay? So all the combinations that make up n with the remaining denominations. In the second case, I say I'm going to use the first denomination only once. Okay, so I know that in the combination, I have used one denomination which is 1 only once. So I subtract that from n, right? And now I need to solve the problem of how to make n minus 1, where 1, remember, is just 1 because it's the first denomination, 1, with the remaining denominations. And then I do it by using the first denomination twice, etc. And I need to go up to n integer division that denomination. So this needs to run because that's the maximum number of times I can use that denomination to make up n. Okay? So the idea here is that I can have the sum of all these answers, because they all make valid combinations, right? For n minus I times the first denomination, okay? Where I is the number of times I'm using that denomination. And this is why I put a comment here. So we will need to have a for loop here, because I need to use that denomination a certain number of times, which is n integer division that denomination.
And that for loop would also be getting called recursively in each
Correct,
layer.
correct. As we then go through the denominations, and our list of denominations gets smaller and smaller.
Is there a difference in terms of how many calls there are between this and the original, or is it just easier to scale up without having to write more for loops?
This is just more scalable in terms of writing.
So not just
But
more efficient.
no. Again, and we can talk about it later because I don't have much time. But yes, so in this case, in other cases, you can make code more efficient by using recursion. Okay, so what's the solution here? Well, this is what we haven't defined here is what is the base case, right? That's the only thing that we are left with. So what's the base case? Well, the base case is when I am left only with one denomination, okay? And with one denomination, I know that that is a valid combination only if that denomination fits an integer number of times into n. So looking at the solution, I mean, this, as you can see, is significantly shorter than those number of loops and is general. What we are doing here is to code up the base case. So if the length of remember, coins is the denominations. If the length of the tuple is 1, this is the base case. and we return 1 if n modulo coins equals 0, which means that that denomination fits an integer number of times into n. Otherwise, we return 0. We have used here a ternary operator, which is a handy way of doing if-else when we want to return a value. Okay? So this will return 1 if this condition is true, otherwise we return 0. Then we need to do the recursive case. Okay? For the recursive case, we need to do that for loop. Okay? And what's that for loop? Well, we start our count of the combinations, and then the for loop runs from I in range n integer division coins, which is 0, which is the denomination that we are using as the first one in this particular list. The +1, as before, is needed only because range is not inclusive, and we need to go up to actual n integer division coins here in the number of times that we can use that denomination. And then we have the definition that we had before. So we keep increasing our count and run this function recursively by using that particular denomination coins 0 I times, and then we call it as a second argument the list of denominations that is the subset that doesn't include the first denomination. Okay? So this is a more complex recursive call, but at the same time is way better than this. Okay? Okay. So there are a couple of cases that, I think I have the time to discuss this. So when do we use recursion? Well, it's a powerful tool when we have intrinsically structures in our problem that we can define recursively. Okay? The idea is that, to summarize, that you need to be able to break your problem into smaller subproblems, that they are the smaller version of the same problem until you hit a base case. Now, this looks very nice, but in some cases, actually, in a good number of cases, recursion is not the best solution. And in other cases, you need to be careful as well, where you think it might be a good solution. It might be, but you might need to be very careful about it in terms of performance. An example where a naive approach to compute the Fibonacci numbers using recursion ends up being actually very expensive is this one. So the Fibonacci numbers, we had defined them earlier, right? We have two base cases because they are defined as the sum of two previous Fibonacci numbers. Okay, so we need to have two base cases. So if n is equals 0, we return 0. If it is 1, we return 1. Otherwise, we have our recursive call. Now, the issue here is that this function calls itself an enormous number of times. And this has to do mainly with the fact that you call the function twice within itself. So every time you go up the stack, you can realize that, it's easy to see that typically when you are computing, let's say, n minus 2, many of these Fibonacci numbers have been pre-computed by other recursive calls, and we are not taking advantage of that, right? So every time we go up, we are recomputing. So let's say Fibonacci n equals Fibonacci n minus 2, which was already called here. So n minus 1 calls again n minus 2, which was already called here. Okay? And so on and so forth. So we go for each call, we go all the way down, and this is a cause of actually an exponential number of calls in this function. So we are recomputing always the same numbers here. And you can try to understand this a bit more. I am putting here a solution. This is not accessible material is just to let you understand that you need to be careful with recursion. Here, we are using a technique called memoization, where we will go over in a lecture in 2 weeks, a little bit more in detail. But the idea here is that what's wrong with the original implementation is that we are recomputing always the same Fibonacci number many times, an exponential number of times. To avoid that, this new version, what it's doing is feeding in a dictionary called the memo. And what this dictionary does is, before getting into the recursive calls, is to check whether we have previously computed that Fibonacci number. And if we have previously computed it, that is getting stored into a dictionary. So I don't need to recompute that recursively. So if I have computed the Fibonacci n minus 1, I just grab the value from my dictionary instead of doing Fibonacci n minus 1 and then recursively n minus 2, n minus 3, n minus 4, and so on and so forth.
So it's like storing in an array, a growing array.
Correct. It grows the dictionary. But the dictionary grows only linearly because you have n Fibonacci numbers.
Every time you access the dictionary is a call that's saved, basically, that you don't have to make.
Correct, exactly. Every time that you access the dictionary is a call that you don't have to do recursively. And so this simplifies the complexity to order n. Okay, so with that, I'm closing up this lecture. We'll go through exercises Friday, a bit more of recursion and a bit more of the exercise which we had on the slide for CSV and iterators.